I was a graduate student at Gifu University. I will present a paper entitled, Learning and Tuning Fuzzy Logic Controller for Vibration Control of a Hydraulic System. First, I would like to explain the construction of the hydraulic system, which is the object of our research. The system consists of a variable displacement axial plunger pump, check valve, elevator and associated hydraulic circuit components. This hydraulic system has been an object of research in many papers. The motion of the plunger has been controlled using various methods including valve control, vibration control based on an accumulator, and others. Most of the control methods used do not offer an effective vibration control mechanism. This is mainly due to uncertainties emanating from the viscosity, compressibility of oil, packing friction, and so on. All these factors bring in non-linearities which are difficult to model, especially in cases where the friction changes from static to dynamic during load manipulation. Such non-linearities are difficult to control from a classical control theory approach. It has been shown that fuzzy logic control can effectively improve the performance of such a system by providing mathematical formulation for linguistic statements and reasoning. The core of the control engine is modeling the action of an operator or controller, without attempting to find a mathematical model of the process, by using fuzzy rules of the if-then type. To accelerate the capabilities of the fuzzy rules, we apply the backpropagation algorithm using the gradient descent method to propagate the error signal. This brings in a substantial improvement in error tracking, resulting in more effective vibration control. The controller configuration is shown in this figure. For simplicity, we assume that the inference system considered has two inputs E and one output V, and a rule based on the simply inference method of the Sugino's type. Here, E is the acceleration error between the output acceleration OA and the desired acceleration DA. E is the change in error, obtained by subtracting the error of the last sampling instant from the present one. V is the compensation voltage, which is summed up with V, to give the reference voltage. The input voltage to the DC servo motor. S is a derivative element. The fuzzy controller consists of a set of linguistic conditional statements or rules which define individual control situations. This simple fuzzy logic controller described here is designed to regulate the output of a process around a given set point. The output is sampled at 10 milliseconds and sent to the controller. The selected fuzzy rules table is shown in Figure A. The factor omega is the object of learning. The initial value of the factors omega k are set to 0. As the basic of fuzzy control is the representation of linguistic statements as membership functions. The membership functions indicate the degree to which a value belongs to the class labeled by the linguistic description. We divide the fuzzy space into three domains for E and delta E as shown in Figure B. For simulation and experimental purposes, the desired pressure inside the cylinder is set to 1.5 MPa, while the temperature is and the sampling period is 10 milliseconds. To achieve the desired plunger acceleration shown in Figure A, we use a reference input voltage shown in Figure B. The evaluation function for learning EP is defined by this equation. When the gradient descent method is implemented to the evaluation function, and it can be expressed by this learning equation. For our system, a modified learning equation given by this equation is needed. An experiment was conducted using the control conditions and this equation. The results of this experiment are shown here. From this result, it can be seen that the square error of the acceleration increases while learning. After 14 epochs, the output has large transient vibration. This means that we need to perform a phase compensation in our control rule table. To do this, we rotate the grade anti-clockwise by 180 degrees, thus constructing a compensated rules table as shown here. The phase compensated equation is shown here. 10K represents the compensated grade of the respective rule table. The output of the plunger after using this phase compensated equation are shown here. This output is achieved after 41 learning epochs. We can clearly see that the square error of the acceleration decreases when learning. Thus, we can conclude that this equation is suitable for our system. But, unfortunately, the plunger output vibrations are not effectively controlled using this expression. And it is also impossible to achieve learning when E equals Z and delta E equals N or P. The control rule doesn't incorporate the change E, and hence we need to modify it to suit zero conditions as well. This is modified equation, which takes into consideration the learning rule to suit zero conditions. For this case, when E equals 0, will be changed by. The results are shown here. From this figure it can be seen that the square error of the acceleration has become smaller. The target square error of acceleration of the control has not yet been achieved. It is necessary to check and assess the learning parameter. The relationship between the coefficient of weight and the training epoch are shown here. We can clearly see that learning is insufficient except for N. The learning equation is further modified to incorporate the parameter alpha such as this. This parameter alpha amplifies the effect of the change in error delta E. Good vibration control is obtained by using this equation for alpha values of from 2.0 to 6.0. From a stability consideration point of view, the best results are achieved when alpha equals 3.0 and after 34 learning epochs. The effect of changing the learning factor eta on the square error were examined and are shown in this figure. From this figure, we can conclude that for small values of learning is slow but attains relatively good stability after the learning epoch. For larger values of learning is fast but very unstable. The best results, at a vibration control point of view, are got when equals 0.05 after 141 epochs, but learning must be stopped after these epochs are reached because the process is divergent thereafter. An experiment was conducted using the modified equation for alpha equals 3.0 and the figures here show the effect of the developed fuzzy controller for 4 different epochs. Good results are obtained after 141 epochs. Comparing the initial and final results, a good improvement has been achieved. Hence we can conclude that the applied type of the learning process is effective for our system. In conclusion, to accelerate the capabilities of the fuzzy rule, we applied the backpropagation algorithm using the gradient descent method to propagate the error signal. The experimental results showed the satisfactory performance and the effectiveness of the proposed learning fuzzy controller. Thank you for your attention.